again. I am Mr. Mohapi, as Nambane has indicated. I'll be the one taking you through the marking guideline for June, paper 1. So before we start, just to add on the few logistical issues that Nambane has just indicated. One, colleagues, for smooth running of this marking discussion, may we please, colleagues, wait until I finish a question for you to contribute or ask questions. And then maybe with question number 2, you can then come in, colleagues, and then ask whatever question that you have. And for any of the options that are not available in the marking guideline that you came across as we were marking your learners, please take a picture of that option and send it to your subject advisors. They will then send it to us. We'll then confirm it, and then we'll send an addendum later today. Thank you very much. I do not know, Mebusi, if there is anything that you would like to say before we start with the discussion. Mebusi?
Thank you, I'm happy. Just for the sake of time. Colleagues, good morning. Please, when you have a question, let us do it with respect. Or when you have a disagreement, let us still do it with respect. Let's treat one another with all the respect. And please don't feel free to put in your options that you have so that we can look at them. Don't just say maybe it is incorrect or whatever, because remember, we are doing it for the benefit of our learners, and we still need to keep our science correct. Thank you, Dr. Mahapi.
Thank you very much, colleagues. Let us get to it. So with our question paper, we have not received many complaints, and then we think that the paper was well received. There were not, we did not receive generally a lot of complaints about the paper, the wording, and all those things. So with question 1, we'll take the options as they are in the memo. There are no changes in the marking guideline. All the options are correct, colleagues. Let us stick to them. Now we move on to question number 2. It was about Newton's laws. In question number 2, I'll be reading the question paper from my side here. It says grade Q with a mass of 15 kilograms is pulled to the right with a force F of 79.8 newtons on a rough horizontal surface. The force is applied at an angle of 25 degrees to the horizontal as shown below. You have the diagram there, colleagues. And then a grade moves at constant velocity. 2.1.1, learners were asked to state Newton's first law of motion in weights. Colleagues, if any of the key weight is omitted.
Good morning. In Welcome High School, in Welcome, we are not getting any sound. And then we have missed that question number 1. I'm not sure if there's anyone else who's getting any sound, but we are not getting any sound from you. Thank you.
Okay, thank you very much, Nambane. Colleagues, I was at question number 2.1.1, where learners were expected to state Newton's first law of motion in weights. We say for this one, a learner can get 1 out of 2, or 0 out of 2, or 2 out of 2. But how will a learner get 1 out of 2? It is when, or if a learner omits any of the key weights. The key weights are those that are underlined in the definition there. If any of them is omitted, but the context is still correct, then the learner will get 1 out of 2. But if everything is correct as indicated in the definition and underlined there, then the learner will get 2 out of 2. We then move on, colleagues, to question number 2.1 2.1.2. With 2.1.2 there, the learners were asked to draw a labeled free body diagram showing all the forces acting on the crate. We have 4 forces acting on the crate there, colleagues. We have the normal force, the applied force, we have the frictional force, kinetic frictional force, and then we have the weight. So if a learner has drawn all the forces, has shown all the forces with correct labels, then a learner will get 4 out of 4. Remember, your force must be indicated with an arrow. If there is no arrow, then a learner will forfeit 1 mark. If you have an arrow without a label, then it is wrong, colleagues. And then the acceptable labels for each of the forces. For applied force, colleagues, we have agreed that we will accept F applied. We'll also accept if a learner writes 79.8, which is the magnitude of the force. And then, colleagues, may you please add there another label that we can accept, which is F, but the A must be a capital letter, colleagues. We can accept if a learner for applied force write FA with a capital letter A. Okay, colleagues, please add that option there for applied force. And then for normal force, we will accept capital letter N. For normal force, we will also accept F normal. We will also accept normal force if it is written in full. For frictional force, yes, we have used FK because it is a kinetic frictional force since it is moving, since our crate is moving. And then if a learner writes small letter F for frictional force, we can accept. If a learner writes F friction, we can also accept if capital letter F and subscript small letter F is written. We can also accept friction in full. We can also accept kinetic friction. We can also accept, colleagues. With the weight, we can accept, or rather we have given the W, small letter W. But if a learner uses FG, we can accept. If a learner uses FW, we can accept. W in weight in weights, we can accept, or the magnitude of the weight of the crate. That is 147 newtons, we can accept. Mg, we can also accept. And gravitational force in full, we can accept, colleagues. If a learner chooses, instead of using applied force, like it is the case for this first option, then the learner now writes the components of the applied force. That is the vertical component. That is the vertical component and the horizontal component. For both the components, if they are correct, then the learner can get 1 mark for those. But in cases where a learner will write the components and also include the applied force, then we will be having an extra force there, then the learner will forfeit 1 mark. I hope that is clear, colleagues. If a learner uses the components and also shows the applied force, then in total, we'll be having 5 forces instead of 4, then the learner will forfeit 1 mark. But if the learner does not use the applied force, but uses the components, then for both components, then the learner will get 1 mark. So acceptable labels, alternative labels for the components of the force. For vertical component, we can use Fy, F vertical, or F vertical. For horizontal components, we can use Fx or F horizontal. That is that for 2.1.2, colleagues. I now move on to question number 2.1.3. Question 2.1.3. Learners, okay. They say here the coefficient of friction between the crate and the surface is X. Then A, learners are asked to give the type of the frictional force that is applicable in this situation. Because here we have 2 types of frictions, colleagues. We know we have static friction and then we have kinetic frictional force. And since this crate of ours is in motion, then we are going to deal, we are dealing with what? With kinetic frictional force. So if the learner writes kinetic, then we can give 1 mark for that. Then 2.1.3b, learners are asked to calculate the magnitude of the normal force acting on the grate. For that, colleagues, we know our normal force will be equal to gravitational force minus the vertical components of the applied force. We do not mark the formula, but the first mark will be on 15, that is the mass multiplied by 9.8 for gravitational force. The substitution, colleagues, not the formula. If the learner is 15 multiplied by 9.8, we give a mark, and then minus, if the learner writes 79.8, that is the vertical component, 79.8 sine of 25 degrees, we give a mark there, and then the last mark will be on the final answer. So 1 mark for substitution for gravitational force, 1 mark for substitution on the vertical components of the applied force, and then 1 mark for the final answer. That will be your 3 marks, colleagues. Okay, I know here for sine, some learners will use cos, then cos will be 90 minus 25. 90 minus 25, that is what? That is 65. If the learner says cos the 79.8 cos 65, I think that will also be correct, colleagues. And then it will lead to the same answer. That is question number 2.1.3b. We now move on, colleagues, to question 2.1.3c. With question 2.1.3c, we have positive marking from 2.1.3b. Here, colleagues, the learners are now asked to calculate the coefficient of friction. The coefficient of kinetic friction, colleagues, we will use Newton's second law. F net is equals to MA. And then horizontally, we are having the horizontal component of the applied force acting there, and also have the frictional force acting there. And because the grade is moving at constant velocity, our acceleration will be equal to 0. So it will be 79.8 cos of 25 degrees minus the frictional force, which is coefficient of kinetic friction multiplied by the normal force, then equaling what? Equaling MA. Then from there, for the right-hand side, we'll be having 15 multiplied by 0. And then on the left-hand side, we'll be having X substituting what? The coefficient of kinetic friction, since in the question there, we said the coefficient of friction is what? Is X. And then your coefficient of friction is there as 0.64. So how do we allocate the mark? If we take right as positive, this is how we'll allocate the marks. For the principle Newton's second law, F net is equal to MA, 1 mark. For substituting your acceleration as 0, or just giving 0 on the right-hand side of the equal sign, colleagues, that will be a mark. And then on the left-hand side, if everything is correct, not forgetting that we have used positive marking from 2.1.3. If everything is correct, for, on the left-hand side, that is 79.8 cos of 25 or sine of 65 minus X multiplied by 113.28 from B, from 2.1.3b. If everything is correct, then you get a mark. And then the value of X will be equal to 0.64. That is if you have taken right as what? As positive. If we take left or right as negative, then the horizontal components of the applied force will be negative and your frictional force will be positive. But we still use the same criteria that we have used, where your principle, that is Newton's second law, will be 1 mark. And then on the right-hand side, if 0 has been substituted for acceleration, or you just have 0, then you can, learner will get a mark. If everything on the left-hand side of the equal sign is correct, then the learner will get a mark. And lastly, the last mark will be on the final answer, where X, your coefficient of kinetic friction, will be equal to what? Will be equal to 0.64. I hope that is clear, colleagues, for question number 2.1.3c. Now moving on to question 2.2. Here, colleagues, we wanted to test the skill of the learners being able to use the proportionalities that we usually get in the multiple choice questions. So here we have a NASA astronaut that was sent to planet Y for a study. While there, the astronaut discovered that the distant planet Y has a mass half that of the Earth and a radius that is twice that of the Earth. Then learners were asked to calculate the magnitude of the gravitational acceleration at the distant planet Y. So because they are looking for the gravitational acceleration, in fact, they are comparing the gravitational acceleration on Earth and that on what? On planet Y. It should be Y here, colleagues, not X. Ne? Please change this. It should be Y instead of X. Okay. So if a learner writes the formula of the gravitational acceleration, which is equal to G, mass of the Earth, radius of the Earth squared, or they use this formula here where they say gravitational acceleration at planet Y is equals to G, half mass of Earth, and then 2 multiplied by radius of Earth all squared. Then for any of the two, a learner will get 1 mark. And then the second mark, if the learner substitutes correctly with the half the mass of gravitational, half mass of the Earth, and then in your numerator, then the learner will get the 1 mark. And then the second mark will come in the denominator if the learner multiplies the radius of Earth by 2 and then all squared. This whole thing, 2 multiplied by 6, 3, 8 multiplied by 6, all squared. Then the learner gets 1 mark, and the other mark will be for what? For the final answer. Let me go through it again, colleagues. Here I said we were testing the skill of being able to do the proportionality questions. If for any of the formulas, here the formula for gravitational acceleration, the learner will get 1. And then the second mark will be where a learner has substituted the mass of Earth with half mass of Earth, which is 5,98 times 10 to the power 24. That is 1 mark. And then the second mark will be on the denominator, where you have 2 multiplied by 6,38 times 10 to the power 6, all squared. That whole thing, colleagues, will have a mark. And then the fourth mark will be on the final answer, which is 1,22 meters per second square. That is question number 2, colleagues, for 18 marks. I'll take a pause for a minute to check if there are any questions on question number 2.
Good morning, everybody. I just want to know, in terms of question 2.2, if they worked with, instead of substituting in the real values for the mass of the Earth and the radius, they worked with ratios in terms of that is now going to be 1/8 or 1/8 times G on Earth. And they then divide the 9,8 by 8, then they also get this answer of 1,22. So they worked with the ratios, but they didn't substitute in the values for the mass and the radius. They used the 9,8, the value on Earth. Will we also be able to give them full marks for that?
Yes, I think that is correct, but because that is basically the skill that we are testing here. I think that will be correct. May you please take a picture of that option and send it to your subject advisor, ma'am, so that it can be included in the addendum that we will send later. From what I'm hearing, it is correct, ma'am. Thank you very much.
Thank you.
Colleagues, good morning again. I'm happy. Please, when you discuss, let us consider the new markers. Colleagues, number 1, I would like you to, when you put a tick to help the learner, put the tick where the correct answer is. And when you put the cross where the learner did not do the correct thing, please put the cross where the answer is incorrect, so that the learner in future knows which part is correct, which part is wrong. Don't put the ticks at the end and give the full marks. And then I'm happy, sorry, please, please, for the sake of new teachers, discuss what positive marking means and up to the last, the answer, the final answer, because the final answer won't be the same as the one that is in the memo. So for the sake of new markers, please do so.
All right, ma'am. All right. Is there any other thing? Okay. Now let me go back to question number 2.1.3, moving on to question number 2. Yes, 2.1.3b to 2.1.3c, just to explain for the sake of new markers what positive marking is. Colleagues, as you can see here, let's say for whatever reason, the learner does not get this answer correct. Learner gets something else here at what? At B. Maybe a learner does not get 113.28 newtons, but continues to use this wrong answer that the learner got here correctly here. And I suspect that many of our learners, instead of saying FG minus the vertical component, some of them or many of them might write normal force being equal to gravitational force only. Then obviously this will be wrong. But if the learner continues with this wrong answer from B, and then they use that wrong answer from B correctly in here for normal force, instead of substituting 113.28, then the learner will substitute, I think it is 147 that we had earlier there for normal force. If the learner just says normal force is equal to gravitational force. If they substitute it correctly here, we'll give a mark. Because they have correctly substituted it, colleagues, then the final answer, you'll then have to put it in your calculator to check what the answer is. If the answer is correct according to that wrong answer that they took from B, then you'll then give the final the mark for the final answer. That is what positive marking means, colleagues. If the answer from B is wrong for whatever reason, and like I indicated, I suspect some of our learners will just say normal force is equal to gravitational force, but then they continue with that wrong answer and then they use it correctly in C. They then substitute it here, you'll give a mark, and then you'll then have to punch that into your calculator and check if they have done a correct calculation. And then if they have done a correct calculation, then you will then proceed to give this mark. That is what positive marking means, colleagues. Thank you very much, Mebusi, and the colleague who has asked a question. Thank you, Tate Nambane. Can we move on to question number 3? Okay. Okay, thank you very much, colleagues. Let's come to question number 3. That is where we were dealing with momentum. Question number 3, 3.1. During a snooker game, 2 balls X and Y collide elastically. Ball X has a mass of 1.56 kilograms and travels at 3 meters per second in a straight line. Ball Y with an unknown mass was stationary before ball X hit it. After collision, ball X becomes stationary and ball Y moves forward at 2 meters per second in a straight line. First question, that is 3.1.1. Learners were asked to explain what is meant by the term elastic collision. This here is a pattern marking, colleagues, meaning here a learner can get 1 out of 2 or get 2 out of 2. So elastic collision is a collision during which the total kinetic energy, we want this with total kinetic energy. If the learner writes total kinetic energy, then they'll get the mark of the object in the system is conserved or stays the same. For this last part is conserved or stays the same, then the learner will get a mark, colleagues. Where do we put the mark? The collision during which the total kinetic energy, but total kinetic energy is what is important, must be there, get a mark. And then this of the object in the system is conserved or stays the same, is where a learner will get a mark. That is where your 2 marks will be, colleagues. So a learner can get a mark for total kinetic energy only, even if this last part is wrong. Or in the system, it stays the same or is conserved, then the learner can get the mark. Let's say whatever the learner wrote something here, but then which is wrong, but then continues to say it's conserved or stays the same, then the learner can get this mark here, colleagues. We have decided that here we are not going to look for context, colleagues. Okay. And then 3.1.2, the learners were then asked to calculate the magnitude of the unknown mass of ball Y. Originally we had we used elastic collision to answer this question as the first option, but then we decided afterwards that many of our learners will use principle of conservation of momentum. So if a learner uses this principle, we will then give marks, colleagues, because we know for elastic collisions, momentum is also conserved. Because of that, colleagues, we've then decided that this principle can be accepted, and then we will take it as the first option. So here, colleagues, if the learner writes the correct principle of momentum, then the learner will get 1 mark. For correct substitution on the left-hand side of the equal sign here, colleagues, where you have 1,56 by 3 plus mass that we are looking for multiplied by 0, because initially Y was stationary. If the learner writes this correctly, then the learner will get a mark for the whole substitution on the left-hand side, colleagues. And this is equal to, because after collision, mass object X or ball X becomes stationary. So we are going to have 1,56 multiplied by 0 plus mass multiplied by 2. For the whole substitution, colleagues will get what? A learner will get what? 1 mark. And then the final answer for they use this principle, the final answer will be 2.4 kilograms. If the learner has done that, colleagues, then the learner will get full marks there. Okay, and do not forget, colleagues, if any substitution is wrong, then the learner will forfeit the marks for the final answer. Even if the final answer is correct there, the learner has written a correct final answer, but if there was a mistake in the substitution, then the learner will get a mark of the final answer. Okay. And then option number 2, if the learner, which was the original option in the memo, colleagues, so because the collision was elastic, we know total kinetic energy of the system will be conserved. Then the total kinetic energy before collision will be equal to the total kinetic energy after collision. We have also accepted that colleagues will take this option. Here we are going to half. Lena has equated the two total kinetic energies, that is before and after the collision. Then on the left-hand side, we'll have half multiplied by 1,56 multiplied by 3 squared plus half multiplied by m multiplied by 0 squared. For the whole substitution, colleagues will give 1. And then Lena has to equate this to half multiplied by 1,56 multiplied by 0 squared, because after collision, x becomes stationary. And then 0 squared plus half multiplied by m that we are looking for squared. And then the final answer, if they use this, surprisingly, interestingly, colleagues, the answers are not the same. And then we can accept your answer if the learner uses this principle here, elastic collision here, as 3,51. If the learner has used this principle, then we can give full marks colleagues of 3,51. Like I've indicated earlier, if any substitution is wrong, then the answer cannot be correct, colleagues. If the learner has maybe got the substitution wrong, the answer cannot be correct. So those are 2 options that we will accept for number 3.1 and 2. Moving on to question number 3.2. 3.2. In 3.2, here we are, our learners were told that car A fitted with crumble zones collide head-on with car B without crumble zones. Car A of mass 1,350 kilograms moves eastward at 20 meters per second before colliding with car B of mass 1,500 kilograms, which is moving at 10 meters per second westward. Immediately after collision, car A moves backwards at what? At 5 meters per second. Then we have a diagram there. Then learners were told to ignore friction. Then 3.2.1. Zama, a physical science grade 12 learner at the scene argues that the driver of car A will be less injured compared to the driver of car B because car A is fitted with crumble zones. Is Zama's argument correct? Learners were then asked to write yes or no. The answer there, colleagues, is yes. And then moving on with 3.2.2, learners were then asked to explain their answer to 3.2.1. And then here we are not going to use if marking, colleagues, meaning in 3.2.1, even if the learner wrote no, we'll then mark question number 3.2 at 3.2.2. We are not going to use a negative marking here, colleagues. The first point that the learner must indicate is that crumble zones increases the collision time or the contact time. The learner stated that for constant change in momentum, and that is the second mark. The third mark will be using the principle will be less in car A. So according to this principle, F net is equals to change in momentum over change in T. The learner must mention this principle, colleagues. If contact time increases, then the net force decreases, hence less what? Hence less damage. So this statement here, in this statement, the last statement, the learner must indicate the principle that they use, and they must also compare the contact time and the what and the net force. So if the learner indicates the principle that they use and also compares the contact time or shows the relationship between the contact time and the net force, then the learner will get the third mark. That is how we will mark 3.2.2. I hope it is clear, colleagues. Let us go through it again. The first mark will be on where the learner mentions that crumble zones increases the collision time or the contact time. If the learner indicates that, then the learner will get a mark. And then the learner then moves on to indicate that for constant change in momentum, because we are going to use a principle with 3 variables there, the other variable has to be kept constant when you compare the two. So for constant change in momentum, if the learner indicates constant change in momentum, then the learner will get a mark. Then the third mark will be where the learner gives the principle and also gives a relationship between the contact time and the net force. Both of them must be their colleagues. The learner can't just say, according to F net is equals to that, and then say, hence less damage. No, the learner has to indicate the principle and use the principle when now he or she gives us the relationship between the contact time and the net force. If the learner does that, then the learner will get a mark. That will be for 3.2.2. I hope it is clear, colleagues. And then 3.2.3. The learners were then asked to state the principle of conservation of linear momentum in width. Here we want 2 or 0, colleagues, meaning everything must be correct. Once we say 2 or 0, it means everything that is underlined must be there, colleagues, unless it is in brackets. Everything must be there. Total linear momentum of an isolated system remains constant, or in brackets is conserved. So 2 or 0, here colleagues, a learner will either get 2 or what, or 0. Total linear momentum of an isolated system remains constant, 2 or 0. That is how we will mark this one, colleagues. Then moving on to question 3.2.4. Now learners were then asked to calculate the velocity of car B after the collision. To calculate the velocity of car B after collision. So learners will use the principle of conservation of momentum. And then for the principle, stating the principle, and we always encourage that the learners use P and use this first part, colleagues, so that they are guaranteed this first mark here.
Mr. Mohapi,
because they might
have
want
you lost
to
your
interpret it and write it like this. Sometimes they do not write the subscripts there, and then they will forfeit this mark. Let's say, for instance, while I'm there, if the learner chooses not to the I-beam, and then learner then omits the subscripts, then you do not know. Maybe a learner writes MVI A plus MVIB. That will be wrong because now different objects will be symbolized by the same symbol. So if the learner chooses this option here, if you are going to give the mark instead of giving it here, you are going to give it here. Then ensure that the subscripts are correct. Because we are dealing with different objects here, they need to be symbolized differently. You cannot have M and M symbolizing different objects. So please be careful when you mark this principle. Hence, we always encourage that our learners to avoid that. Our learners must write the principle as indicated here by the first mark, colleagues. But then you can give either this mark either here or there. But this one will only give it if everything, including the subscripts, is correct. So that will be the first mark. The second mark will be for the correct substitution on the left-hand side. By correct substitution, yes, Yes, Mimi. Ntate Nambane. Ntate Nambane. Colleagues, am I still audible?
For now, you're audible, Baba.
Ntate Nambane.
Yes, Mr. Nambane, we can hear you, but we cannot hear Ntate Mohapi. While checking Ntate Nambane, can I go to question?
Colleagues, am I still there?
312.
Even it seems like I'm alone in the meeting. Hello, colleagues, am I still there? Mr. Nambane.
The vessel's bron cluster can hear you fine.
No, Ntate Nambane, I was referring to that question 312. Ne? Unfortunately, cannot be moved, maybe shown on the screen. But that option number 2, it shouldn't be an option per se. It should be an accept. The thing is, even though we are saying that the collision, it is elastic, but we have to remember that to prove, we are using only this to prove, but to calculation for the mass, then the answers, it is not going to be the same. Because
Yeah. Yes, I'm hearing that. Yes, that I can hear you. Can you hear me?
can I continue?
Can you hear me now?
Yeah, we can hear you. Can I just maybe finish off what I was saying and then we continue? Yeah, what I was saying is this option number 2 here, it shouldn't be an option per se. It should be an accept.
You can hear me now.
Sorry?
Thank you.
Yeah, it shouldn't be an
All
option.
Right, thank you very much. Okay.
Yeah, should be an accept.
All right.
Because
but,
some of
I was not yet done, I think, with 3.2.4. Ne? Maybe I just.
Okay.
Yes, Alina, I'm with you. Okay, thank you very much in that day. Before Ntatensia comes in, may I please conclude 3.2.4, so that Ntatensia, when it comes, then. Yes, yes, that is your fin of. Ntate Nambane. I am sharing now, Ntate Nambane. I would like to hope so that the Nambane just share. And Ntate Nambane, can you see my screen? Okay, colleagues, if you can see the screen, this is, I believe, where we are. Let me once again apologize for this challenge.
Sorry, Wesselsbron can't see a screen.
is not up. I wonder what the problem now. Maybe I should close it and then try to share it again. Is it still not up? Okay. 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 Let me share again that. Okay. What is happening now? Still nothing. Okay. It's fine. It's fine. It's fine. It's fine. Let me try this. Okay. Let me for one last time check if it will now be shared in the day. Let me check one last time. Okay, okay, nice. Yes.
Sorry, from Wesselsbron, the screen is visible now.
Alabocha, screen is visible. Thank you. We never had anything that in Nambane from number 2 and multiple choice. Thank you.
Yeah. Okay. Okay, thank you, Mr. Nambane. Now, what I was referring to in the memo that Ntate Mohapi is using, colleagues will see that for that option 312, the conservation of momentum is used as the first option. So the learners need to calculate the conservation of momentum. Now, this one, which is appearing on the memo, shouldn't be option number 2. It should be an accept. We're accepting it because we have already given the memo the way it is. But when we prove this, we cannot use this because some of the matter, it is lost as energy. Hence, we'll see that there will be a change in the masses. The masses will not be the same. In this case, we'll see that it is having a bigger mass because of that part of the energy, which is also involved here. So even though we are saying kinetic energy, here it is involved. It is not only kinetic. We are using this just to prove that there is an elastic collision. But in essence, we cannot use this to do that calculation. So when we go back to teach our learners, please let's rectify this. This is just an accept because of the issue that in the statement there was an elastic collision which was there. But we cannot use it to calculate for that particular question there. That is what I was just referring to. So it is an accept and not an option. Thank you, Bob.
Thank you very much. All right, Ntate Nambane.
My apologies, leaders. I think I'm I have a problem here. I've been here since 8. It was said the screen was not there. I also didn't see it, and rectifications were being made. And when it comes at question 3. Right now it has been referred. We are on something like 3.4. My screen is on 3.11 up to 3.21. So even at the present moment, the screen is not on what is being discussed. Thank you.
Nambane, can you hear me now? Nambane. Yes, may you move the screen down to that option. That question 3 point. That is the last question there. 3.2.4. Yes. So, and thank you very much, Ntatine. Colleagues, once again, I'm very, very sorry for all the inconveniences. With 3.2.4, there we said that learners will use the principle of conservation of linear momentum, and then 1 mark will be on the principle. The second mark will be for the correct substitution on the left-hand side. That is 1,350 multiplied by 20 plus 1,500 multiplied by -10. That is if it has been taken as positive. And then the second mark will be for the substitution on the right-hand side of the equal sign. 1,350 multiplied by -5 plus 1,500 multiplied by final velocity of B. And then the final answer, colleagues, it must be with what? With direction. So final velocity of B will be 12.50 meters per second eastward. So that is what the final answer will be. So if the learner gives the final answer without the direction, then the learner will forfeit that mark, because here learners were asked to give the velocity, not the magnitude of the velocity, colleagues. With words taken as positive, same criteria will be used there. The only thing is that on the left-hand side, your 20 will be negative now and 10 will be positive. And on the right-hand side of the equal sign, 5 will be positive instead of being negative. That is the only difference between the two options that we are having. So that will be that for question number 3. And then it is 16 marks. So the corrected memo will then be distributed, colleagues. Please do not worry, especially for that question here, 3.1.2 that Ntatine has just explained. So the corrected memo will be distributed. Thank you very much, Ntate. I do not know if there are any questions on question number 3.
All right, thank you so much, Ntate Nambane and Ntate Mohapi. The question was on that definition where it asks for total linear momentum, and then the question has the word linear. Now, do you need in this 323, do you need that word linear to be there? Or if it's omitted, just please clarify there.
I think the word linear is important for this for this principle, colleagues. How is it given in the examination guideline? In the examination guideline is given with a linear. So the word linear is very, very important because we are dealing with object of motion in a straight line when we deal with this principle. So that word is important. That I think it is part of the examination guideline. Mm-hmm. Okay, colleagues, let us now move on to question number 4. We'll try to rush. I know we have lost a lot of time, and apologies once again. Question number 4, that is vertical projectile motion. A ball of mass 250 grams is thrown vertically upwards with a velocity of 12 meters per second from the edge of a building with height h. The ball hits the ground after some time and then bounces off the ground and reaches a height of 25 meters. The position time graph for the below represents the motion of the ball from the instant it is thrown until it reaches the height of 25 meters per second. Then the first question, 25 meters. Then the first question, that is 4.1, learners were asked to define the term free fall. So if any of the keyword is omitted in correct context, colleagues, we can give 1 mark. As you can see there, the definition is motion during which the only force acting on the object is gravitational force. So if any of the keywords is omitted there, then the learner will forfeit 1 mark. So motion is one of the keywords, only force is also one of the keywords, and then gravitational force is another keyword. So if any of those is omitted in correct context, colleagues, we can then give 1 mark instead of 2. I think that is clear. Maybe the learner, instead of saying motion, the learner will say object. In the correct context, colleagues, we can give 1 in that case. So, but the word only must also be there. And then the other one, but then if the learner then talks about a different force, then you can see in that case, then the context will be lost. If the learner, for instance, says a motion during which the only force acting on an object is applied force, for instance, I'm just making an example, then the context has been lost there. Then that one will be 0, colleagues. I hope it is clear. So we need to look at the context, colleagues. Things must be related to what? To the vertical projectile motion or the motion of a projectile. Okay, we can now move on to 4.2. So now we are getting to the calculations, colleagues. We thought that we should draw this diagram to help us with the options that we are having here. So we then said the motion of an object will be from point A, and then it moves at maximum height will be point B, and when it returns to the point of projection, that will be point C. When it hits the ground, that will be point D, and then from the ground to the height after bouncing, that will be point E, so that we deal with motion in portions. For instance, we'll say we're looking at the motion from point A to point B. We think this is a very good teaching tool that we can use when we deal with vertical projectile motion, that you deal with motion in portions. You'll say motion moving from point A to point B. When you use that, you'll know whatever that you are moving from, the point that you are moving from will then be a point where you'll have your initial velocity. The point that you are moving to, that is where you'll have your final velocity. So if you are saying, I'm taking my motion from point A to point B, then whatever velocity you have at point A will be your initial velocity, and the velocity that you will have at point B will be your final velocity. So this is the diagram that we are going to use to help us with the options that we are having in this question. So 4.2 says, it takes the ball 4 seconds to reach the ground after being thrown vertically upwards. Then 4.2.1, learners were asked to calculate the height of the building, which is h. So option number 1 there, to calculate that height, we say we are going to take our motion from point A to point D, taking upwards as positive. If you look at your motion from point A to point D, from point A to point D, the total time is 4 seconds. And then if we use that formula, delta y is equals to VI delta t plus half A delta t squared, then initial velocity, that will be velocity at point A, that will be 12. And then the time it took from A to D will be 4 plus half. And then we know when we have taken upwards as positive, our gravitational acceleration will be negative 9,8, then multiplied by 4 squared. Then your answer will be, you'll get negative 30.40, but that is not where you will give your mark. You know, the learners must do what? Learners must interpret that answer and then give us the height being equals to 30,40 meters. So the first mark will be on the correct formula. The second mark will be on 12 multiplied by 4. The third mark will be on half multiplied by 9.8. Half multiplied by 9.8 multiplied by 4 squared. And the fourth mark will be on height, where the learner has interpreted the answer. Because here we are calculating the displacement. So the learner has to interpret the answer and give us the height. So the answer will be on H, or the height being equals to 30,40 meters. So still taking our motion from A to D, now taking down as positive, then we'll have negative, because at point A, the initial velocity is going up, then we'll have negative 12 multiplied by 4 plus half multiplied by 9,8. 9,8 will be positive now that we have taken upwards as what? As negative. Then downwards has been taken as positive. Then we'll have that half multiplied by 9,8 times 4 squared, and then H being equals to 30.40 will be our fourth mark. That is option number 1, colleagues, to get this thing. Option number 2, if we can go up a bit in the day, Nambane. Option number 2, it is where now we are going to take a bit motion, our motion bit by bit. We'll be moving from A to C, C to D, and then we then do our calculation. So if we are going to take our motion moving from C to D, then it means that we'll then need a time that the object will take moving from C to what? To D. Hence, we started by calculating the time the object will take to move from A to C, which is 2,449. And then we subtract that from 4, then we get 1,551, but there is no mark for calculating that time. Then if the learner gets that correctly and then substitute it correctly here, taking the motion from C to D, you know, from point C in our diagram, the velocity at that point will be negative, because now our object is going down, and then we have taken upwards as positive. At that point, which is point C, our velocity will be negative 12 multiplied by the time that we have calculated there, and then plus half multiplied by 9,8 multiplied by 1,55 squared, which is the time the object will take to move from point C to point what? To point D. And then the height will be equal to 30.40 as in option number 1. So there is no mark in calculating the time. So the learner can use that option, it's okay, but there won't be any mark in calculating that time. Okay, and then the downward is just the opposite of what we had there for upwards being taken as positive. Still moving from C to D after calculating the time. You start first by calculating the time the object takes from A to C, and you subtract 4 from that. Then you'll get the time the object will take moving from C to D. And then now that we are moving down, that 12 will be positive because the object will be moving downwards. And then your gravitational acceleration will be positive with the time from C to D being 1,551 seconds. And then if everything is substituted correctly, we'll have 1 for the formula, 1 for first part of the substitution, that is 12 multiplied by 1,551 plus half multiplied by 9,8 multiplied by 1,551 squared. And then the interpretation of the answer, which is height Yarona is equals to 30.40. That is option number 2. Moving on to option number 3. And let's move up, please. With option number 3, this is where a learner will first calculate the final velocity, the velocity that the object will hit the ground with. Then, if the learner chooses to use the option where he or she will, there's someone with a mic on. Okay, so thank you very much. For option number 3, that is where a learner will first calculate the velocity that the object will hit the ground with. So the learner will then have to take the motion moving from point A to point D, and then calculate the final velocity at point D. If the learner does that, then they will have that formula VF is equals to VI plus 80. And then the initial velocity at point A will be 12, and then plus, because we have taken for the first part, we have taken upwards as positive, that it will be negative 9.8 multiplied by 4, because the total time it took from point A to point D is 4. Then they will get their velocity as 27.2. They then use that velocity of theirs in this formula, that is VF squared, which is equal to VI squared plus 2A delta Y. The final velocity will be the velocity it hits the ground with, which is 27, but that 27 is downwards. So it will be negative 27,2 squared plus initial velocity moving from A, that will be 12, which is positive because at A, the object is going upwards. 12 squared plus 2 multiplied by negative 9.8 delta Y. Then the height interpreted there will be 30,40 meters. Then the downward part, still the same as that one, only difference is the signs. Here your initial velocity will be negative, and then your gravitational acceleration will be positive, and then you still get 27.2. And then when you substitute into this formula, VF squared is equals to VI squared plus 2A delta Y. You'll then have 27,2, which is positive squared, being equal to negative 12 squared, and then plus your gravitational acceleration will be positive. If you take downwards as positive, then the interpretation will then lead to our height being equals to 30.40. That is option number 3, that Nambane. If we move down, if we can move down, please. Option number 4, still there we have the final velocity at point D, the same way that we have calculated the final velocity in option number 3. We'll use that final velocity, but now we will be moving from C to D. If you move from C to D, then your initial velocity will not be positive 12, but will be negative 12. And then we'll then have negative 27, which is the velocity that it will hit the ground with, squared being equals to negative 12 at point C squared plus 2 multiplied by negative 9.8 delta Y. Then your final answer will be 30.40. And then the opposite will happen when you take down as positive. Everything will be positive, because now you'll be moving from C, which is a point where your object will be moving downwards, and then as it hits the ground, the object will be moving downwards. So the final velocity as it moves downwards will still be positive. And then your gravitational acceleration will also be positive. And then the learners will then interpret that your height will be equal to 30.40 meters. So that is option number 4. With option number 5, because now our learners have done the principle of conservation of mechanical energy, we thought that we can include this option also. So here, if the learner uses this principle, with the velocity that we have calculated initially there in option number 3. Velocity at point D will be 27.2 meters per second down. And then we use the principle of conservation of mechanical energy. We have the mass of the object, which is 250 grams. So the learner will then have to substitute that, in fact, convert that to kilograms by dividing by 1,000 and then multiply by 9,8. If you are multiplied by 9,8 and then multiplied by 0. If you take that as your reference point, that will be 0. And then initial velocity at A, there will be what? Will be 12. Fine. And then on the other side, when you go down there, we'll have what? 0.25 multiplied by 9.8, which will be the height. But you can see that height, we are moving from A, moving downwards, which is still fine, colleagues. And then plus half multiplied by 0.25 multiplied by 27.2, which is the velocity it is the ground width squared. And then your height after interpretation will get 30.4 meters. So here, how will we mark? For principle of conservation of mechanical energy, we'll get 1 mark. Correct substitution on the left-hand side of the equal sign. All those values must be there. Then the learner will get 1 mark. And then on the right-hand side, if the learner substitutes correctly, then the learner will get another mark. And then the final mark will be 30.40 meters. And then we move on to option number 6 in that Nambane. Option number 6, these are the energy principles. If we have learners getting to this point, then it's okay, colleagues. Please look at what the learner has done and then mark. Please do not ignore these options. So for this one, for option number 6, here we are using work energy theorem, or the learner will use work energy theorem. We know with the velocity that we have calculated in option number 3, the final velocity will be 27.2, and then there we will then be having what? We'll be having initial velocity of ours being equal to 12, final velocity 27.2, and then on the left-hand side we'll be having work done by gravitational force, since it is the only force acting on an object. So work done by gravitational force will be equal to the total net work done on the object. So for that principle, work net is equal to change in kinetic energy. A learner will get the mark. For correct substitution on the left-hand side, you know the masses will cancel each other out. Then correct substitution on the left-hand side, a learner will get 1 mark. Correct substitution for the whole substitution, colleagues, on the right-hand side, then the learner will get a mark, and then the last mark will be on the final answer. For option number 7, more or less like option number 6, it's just that the learner now chooses to use work done by non-conservative forces. If the learner chooses to use work done by non-conservative forces, we do not have any non-conservative forces acting on the object, which means that on the left-hand side, we'll have 0. And then on the right-hand side, we'll have half into change in velocity, which is what? Change in velocity V F squared, 27.2 squared minus 12 squared plus 0.25 multiplied by 9.8 and change in height. That is the height that we are looking for. Change in height will be using your reference point, maybe from up, down, then your initial height, if that is where you are moving from, or initial displacement, that is where you are moving from. Initial position will be at point A, moving down. That initial position will be 0, and then to the ground there will be your final position. And then you interpret that into your height, which is 30.40 meters. That is that for question number 4.2.1. That Nambane, I believe. So can we move on to question 4.2.2? Okay. So question 4.2.2, learners were asked to calculate the distance the ball and the distance between the ball and the maximum height reached after the bounce. That is the distance that the learners were asked to calculate. So here, colleagues, we have drawn again a diagram to try and explain how you come up with that distance. It is the distance between the ball after 3 seconds. Yeah? The distance between the ball after the ball has traveled 3 seconds and the height it bounces to. So as you can see from the diagram, we are having our ball moving from point A to point B, then from point B to point C, then it moves to a certain point there where it has traveled for 3 seconds. And after the bounce, it moves from D to what? To E. So D to E, the distance there is what? Is 25. And then from C to, you can say from C to a point where it has traveled 3 seconds will be 8.1 meters. We'll show that in the calculation, colleagues. And then you just want the difference there between the two. Let us go to options in that Nambane. Remember here, colleagues, we are using a positive marking from question 4.2.1. So for option number one, after 3 seconds, we'll calculate the distance or the displacement that our object has traveled afterward after 3 seconds. That is the first part of the calculation. So you calculate that displacement. That displacement will be using, for option one, using the formula delta y equals to vi delta t plus half a delta t squared. Then if you move from point A to that point where it has traveled for 3 seconds, we'll have 12 multiplied by 3 plus half multiplied by negative 9,8. Since we have taken upwards as positive, then our g must be, or our acceleration must be negative, multiplied by 9 squared. Then we'll get our displacement, because after 3 seconds, our object will now be moving downwards. And because it will be moving downwards, then our displacement will be negative. Hence, we get negative 8.10 meters. But the distance that we are looking for, it is that distance, that the number, if you could go up a bit. Not up a bit, where we have that diagram, that the number. Yes, here. So that is the displacement of 8.1. And now we are looking for the distance between that 8.1, the displacement as it moves down, and the 25. So as you can see here, when you add 8.1 to that distance to 25, then they must give you what? 30.4. They must give you 30.4. Then we just look for that distance there by saying 30.4 minus 8.1 minus 25. And then that will be the distance between, between the ball and the maximum height reached after what? After the bounce, when the ball has been in air for 3 seconds. And then that distance will be 2.70 meters. So option one, with downwards have taken as positive, you know, it is only the signs that will change, but the principle is still the same. The criteria that we have used there, colleagues, will still be the same. How do we mark? One for the formula, that is the first mark. The second mark will be the formula, that is delta y equals to vi delta t plus half at delta t squared. That is 1 mark. And then the correct substitution for the whole substitution, colleagues, 12 multiplied by 3 plus half multiplied by negative 9,8 multiplied by 3 squared. If everything is correct there, then the learner will get a mark. And then the learner uses the answer that they get through this formula correctly in this distance formula, if you like, where now they have to calculate the distance, where they will be saying 30.40 minus 25 minus 8.10. Even if the learner gets that 8.10 wrong, let's say for argument's sake, the learner gets that wrong, but they substitute it correctly here. That is correct transference within the question. If that is the case, then the learner will get a mark there, but the learner will forfeit the mark for the final answer. Let me repeat that, colleagues. Here we are going to have a mark for the formula, mark for correct substitution. Everything in the substitution must be correct. But if there is a mistake in the substitution and the learner then gets a wrong answer, the learner does not get 8.10 there. And then they take that wrong answer of theirs and then substitute it correctly here where we are now looking for the distance. Then you can give a mark there for correct transference. But then the learner will forfeit the mark for the final answer. I hope that is clear, colleagues. That is option number 1. If you can move up a bit in that day, Nambane. Moving on to option number 2. Here, the learner will be looking for a velocity first after the ball has been in air for 3 seconds. So moving from point A to a point where it has been in air for 3 seconds, then their velocity, they will use the formula VF is equals to VI plus A delta T. Then velocity after 3 seconds will then be given by 12 plus into negative 9.8 multiplied by 3, which then gives or should give them 17.4. But we do not have a mark there. Then the mark will come here. Now the learner uses the formula to find that 8.10. Somehow the learner must get to 8.10. Then they use the formula VF squared is equals to VI squared plus 2A delta Y. And then they substitute 17.40 correctly into the formula, and they also substitute 12 correctly into the formula. And then they find, and then plus 2 multiplied by negative 9.8 delta Y. And then their delta Y becomes negative 8.10. And then the very same thing that we have said earlier, if for whatever reason the learner got something, did not substitute correctly and then got that delta Y of 8.10 wrong, but then they substituted correctly here where they now need to find the distance, you can give that mark. That will be the mark for correct transference. And then if that is the case, but the learner will then forfeit mark the final mark for the final answer. So when you take down as positive, we'll still get what? 17.4, but now your 9.8 will be positive and your 12 will be negative. Remember, we are moving from A. I get at point A, that is where your object is moving upwards. So initial velocity at point A will be an upward velocity. Hence, it is negative where we take down as positive. Yes. And then we then move on to VF squared being equal to VI squared plus 2A delta Y. Then if the learner substitutes correctly, that's 17.4. And then the initial velocity is also substituted correctly there with negative 12 squared plus 2 multiplied by positive 9.8, since we are now moving downwards. Then we'll get 8.10. And I will repeat this again. If that 8.1 is not correct, but it is correctly used, where now the learner has to find the distance, you can give the mark for substituting, and then the learner will forfeit that mark for the final answer. That is option number 2. Option number 3, that is Nambane. Option number 3, we are taking from what we had there, but now we are moving from where? From C to 3 seconds. We are moving from the velocity that we have calculated in option number 2 there. So in this case, you know at point C, your object will be moving downwards, so your initial velocity will be negative 12 if you take upwards as positive. And then 17, remember 17.4, it is the velocity when the object has been in air for 3 seconds. But after 3 seconds, then we know our object will be going down. Hence, that 17 is substituted as what? As negative. Then if you substitute, so you'll get that negative 8.10, and then the learner then substituted that where now the learner wants to find the distance, and then the final answer will be 2.70. If it is wrong, but it's substituted correctly, then the learner can get a mark, but forfeit 1 mark for the final answer. So the very same thing can be done with downwards being positive. Then we'll have mark for the formula, mark for the correct substitution. Remember, correct substitution here, everything must be substituted correctly. everything must be substituted correctly. And then the second mark will be where now the learner wants the distance and then the final answer. That is option number 3. If we could go down into the Nambane, that will be question number 4.2.2. Then we move on to question 4.2.3. Here now, learners are asked to calculate the velocity the ball leaves the ground with after the bounce. Velocity, the ball leaves the ground with after the bounce. After the bounce, we know it is going to go to a maximum height of what? Of 25. So we want the initial velocity option 1. We are now moving from point D to point E. So moving from point D to point E, now it is going up. We want the velocity that it goes up with. So it will be VF squared being equals to VI squared plus 2A delta Y. That is the first option that we will use. And then we know the maximum height, our velocity is 0. And then we are looking for that initial velocity, the one it leaves point D with. And then that will be VI squared plus 2, because we have taken upwards as positive here. 2 multiplied by negative 9,8. And then 25, because now our object will be moving upwards. So to cover that 25, our object will be moving upwards. Therefore, 25 will be an upward displacement, and we have taken upward as positive. Therefore, that 25 has to be positive. And then if we have done that correctly, or a learner has done that correctly, then they should get an answer, which is initial velocity being equals to 22.14 meters per second, and then upward. Because here they were asked to calculate velocity, we want the answer or the magnitude and what? And direction. If the learner just gives the magnitude, then the learner should forfeit that mark of the final answer. So here we want magnitude and direction. So if for option 1, the learner, option 1, if now they take upwards as negative, then downwards as positive, that the number if you could go up a bit. So we will still use the same formula, VF is equals to VI plus that number if you could go up a bit. But it is the same as the one that we are having there, colleagues. It is VF squared is equals to VI squared. That is where they have taken upwards as positive. The number has he hit that part, but I hope you can follow, colleagues, because it is just the change in what? In direction. Let us look at option number 2. Option number 2, now we are taking our motion if the learner chooses to take his or her motion moving from point E to point D. So if the learner chooses to do that, and then they calculate the time it will take that ball to move from point E to D, if that is the case, then we'll have, the learner will then calculate firstly the time it takes the ball to move from point E to point D. If they do that, because now they are moving from E to D, then that displacement of 25 will be negative, because if we have taken upwards as positive. So you are moving from E to D, then the object will be moving downwards, and downwards has been taken as positive for the first part. Then 25 will be negative. And then because that is the maximum height that we are having there, the initial velocity will be 0. And then they will then have to calculate the time. The time will be equal to 2,58767 seconds. But we do not have any mark for that part. The mark will come for the second part of that option, where now the learner uses the formula VF is equals to VI plus A delta T. And then we have final velocity there being equals to what? 0. And then initial velocity will be VI plus what? Plus negative 9,8, and then multiplied by the time that they will have calculated there. So that will be initial velocity 22,14, like we have found it in option number 1. Same when you take down as positive. Down as positive if you are moving from E to D for the first part. This E to D is for the first part, colleagues. So just to calculate the time. So it is E to D, then the time will be 25 will be positive in this case. It is positive because now we have taken down as positive, and to cover that 25, if we are moving from E to D, then the object will, or the ball will be moving downwards. So it will be a downward displacement, hence it is positive. So we'll start marking from the second part of that option, where we now have VF being equals to VI plus A delta T, and then we'll have 0 initial velocity, and then 9.8 multiplied by 2, or the time that the learner will have got in the first part of this option. And then initial velocity will be 22.14 meters per second upwards. That is that for question number 4.2.3. Like I indicated, colleagues, if you have any other options that you came across as you were marking, please take a picture of those options and then send them to your subject advisors. Then we'll then compile an addendum that will be distributed with the memo that we had earlier. Now we move on to question 4.3. We are then, or learners were then told that the ball is in contact with the air with the ground, sorry, for 0.2 seconds. Then 4.3.1, learners are then asked to define the term impulse. Here we are going to have what, colleagues? We are going to have path marking. The product of the resultant or the net force acting on an object and the time the net force acts on the object. So the first part that we will mark is the product of the resultant or net force acting on an object. That is the first part. We'll give 1, and the time the net force acts on the object, that will be where the second mark will be. We've then decided that we can accept if the learner, but please, we should not teach our learners this thing. That is why, colleagues, we should not, please, we are all discouraged, please, to distribute the memo to our learners, because our learners will then take these things that we accept during the discussions as correct answers. So please do not distribute the marking guidelines to learners. Let us go back and discuss the memo with the learners. And as we discuss, we must emphasize that to our learners that they need to give the definitions as they appear in the examination guideline. But for the purpose of marking, we can accept if a learner says impulse is equals to change in what? In momenta. Okay, then moving on to 4.3.2. For 4.3.2, we have positive marking from 4.2.3. If we could go up in the Nambane, we have positive marking. I hope by now everyone understands what positive marking is. Then you'll have to take the answers that the learner got, even if they are wrong. If they are used correctly here, then you'll have to punch everything into a calculator and check if the learner has used them correctly. If they have used them correctly, then the learner will get the full marks. So here, learners were asked 4.3.2, learners were asked to calculate the magnitude of the force exerted by the ground on the what? On the ball. So to calculate that, we are going to use the impulse theorem, momentum theorem. So first part, we are moving from A to D. If you move from A to D, take into consideration the positive marking from 4.2.3. So the learner will calculate velocity at D. And then after calculating velocity at point D, they will then say F net delta P is equals to change, the delta T is equals to change in momentum. And then F net multiplied by 0.2, because our mass was given in grams, we'll then have to divide that by 1,000. And then change in velocities. What are the velocities, colleagues? The changes in velocity, initial velocity will then have to be the velocity the object hits the ground with. That is the velocity at point D. The velocity the object hits the ground with. That will be the initial velocity. And then that velocity will be 27.2. And then final velocity will be the velocity the object leaves the ground with after the bounce. Just there. The changes in velocities, we are looking there for them at the point of contact there. So the one it hits the ground with will be your initial velocity, and the one it leaves the ground with will be the final velocity. So how do we mark this? Looking at option number 1, taking motion from A to D. And then this part of A to D, it is where we now want the velocity the object will hit the ground with. We'll have VF is equals to VI delta T, and then velocity at D is equal to 12 plus negative 9,8 multiplied by 4, because we have taken upwards as positive, hence 9.8 is negative. Then we'll get negative 27.2. We have calculated it somewhere, but then the learner has to show it here because it was not asked there. The learner might have used it, but it is not the answer that was asked in the previous questions. So here we need the learner to show us how they get that 27.2 for them to get the first mark in this option. And then the learner will then use the impulse momentum theorem. With the impulse momentum theorem, for that theorem, a formula F net delta T is equal to change in momentum, then the learner will get 1. And then substitution on the left-hand side, that is F net multiplied by 0,2, the learner will get 1. Conversion of the mass from 250 grams to kilograms, then the learner will get 1. Even if the learner just write 0,25, it's fine, colleagues, you can give that 1 mark. And then here the change, we said final velocity, it is the one that it leaves the ground with that we have calculated in 4.2.3. So just check the answer of the learner from 4.2.3, and then check if the learner has substituted that answer correctly here. So the correct one is 22.14, but if the learner substitute whatever that they got in 4.2.3 correctly, and then subtract the one that they will have got here when they were looking for velocity of at point D, of the ball at point D, then substitute it correctly. By correctly, I mean with the direction, colleagues, because we are dealing with velocities. So it has to be minus into negative 27.2. If we have correct substitution for the velocities, initial and final, taking into consideration the positive marking from 4.2.3, then the learner will get 1 mark. And then the final answer will be that of the net force being equals to 61.67 newtons. That will be option 1 for this question, colleagues. I hope it is clear. Then you can take down as positive. You'll still have to first take or calculate the velocity it will hit the ground with. Then the substitution in calculating velocity the ball hits the ground with. That substitution has a mark. And then mark for the formula, another mark for substitution on the left-hand side, and then another mark for the conversion, another mark for the velocities, correct substitution of the velocities. But now the signs for the velocities will change, because the first velocity or the final velocity will be the one that it leaves the ground with, will be an upward velocity. Then it has to be substituted as negative, and then minus the one it hits the ground with will have to be substituted as positive 27.2. If that substitution is correct, then the learner will get the other mark, and then the final mark will be on the net force being equals to 61.675 newtons. Remember, we can also accept if the learner rounds off to 2 decimal places. We can go down that Nambane. Option number 2, still, colleagues, we need our learners to do what? To find the velocity the object will hit the ground with. But here now, the learner will not use the formula with the time, will now use the formula with the displacement. We have calculated that displacement, that height, if you move from A to D. In the previous question, that is 4.2.1. We can also use the positive marking there from 4.2.1 for this option. And if the learner uses that correctly, then the learner should end up with 22.7. And then the criteria that we have used for option number 1 will still apply here. But the only difference here is to find the velocity at point D, meaning the velocity that the ball will hit the ground with, will be different. In the previous option, the learners used the formula with time. Now the learners are using the formula with what? With displacement, that we have calculated in 4.2.1. So just check if the learner uses this formula and then substitute the answer that they got in 4.2.1, then you can give a mark there. Then the mark will be not on the formula to find the velocity it hits the ground with, but the mark will be on the substitution into that formula. It is very, very important that we note that, colleagues. There's no mark on the formula to calculate velocity it hits the ground with. The mark is on the substitution into that formula to find what velocity it hits the ground with, and the other formula will be on the impulse momentum theorem, and then like we did earlier, it will be on the left-hand side, that is where F net multiplied by delta T. You'll get a mark, conversion of your mass, a mark, and then the difference in the velocities, a mark, and then final answer, that is 61.675 newtons for the net force. We want only the magnitude here. So that is option number 2. With downwards as positive, the same thing, colleagues, just the change in what the difference in the signs. You know, you are moving from A, at A, object is going up, then we'll have negative 12. And then because that 30.4, it is a downward displacement. Our object covers that height moving downwards. Therefore, it will be positive if we take downwards as what? As positive. But the principle or the criteria will still be the same. What is to note here, colleagues, which is very, very important, is that for the first part where the learner has to find the velocity it is the ground with, there is no mark on the formula. The mark is on the substitution into that formula. That is what is key. Then option number 3, option number 3, now the learner is moving from C to D. If the learner chooses to move from C to D, aim, the first part, the aim is to find velocity the object hits the ground with. That is the first part. But there is no mark on the formula to find the velocity it hits the ground with. The mark is on the substitution into that formula. So if the learner takes the motion from C to D, then instead of positive, and then we have taken upwards as positive, then we'll have negative 12 squared plus 2 into negative 9.8, and then multiplied by negative 30.4. The issue of negative 30.4, it has already been explained. So it is negative because we have taken up as positive, and to cover that 30.4, your object will be, the ball will be moving downwards. So if you take down as positive at point C, the object is moving down, therefore velocity at point C will be positive. Hence it is positive 12 plus 2 multiplied by 9.8 multiplied by 30.4. And then you continue like that with the marking, colleagues. I hope everything is clear. Okay. If you look at option number 3, just before you move on that the number, I think there is a mistake there with option number 3 where down has been taken as positive. You see that the substitution of the velocities, that the number, if you could point there, of the change in velocities going down in the brackets. So at that point, that one, the negative has to be on 22.14. And 27.2 must be positive. Colleagues, please note that. 22.14 must be negative, and then minus what? Minus 27.2. Okay. That is that for question 4.3.2. Now we move on to question 4.4. 4.4, positive marking. We'll have positive marking that the Nambane, you rushed, just go up, yes. Okay, we'll have positive marking from question 4.2.3. So here learners are asked to draw the velocity versus time graph representing the motion of the ball from the moment it is thrown until it reaches the maximum height after the bounce. And then the learners are asked to indicate the following in their graphs. Firstly, the velocity with which it is thrown, that is the 12, and then velocity with which it leaves the ground with, not the one that it hits the ground with, the one it leaves the ground with, and then the time it reaches the ground, and then the time it leaves the ground. That is very, very important, colleagues. So if we take up as positive, because initially our object was moving up If you could go up in the day, Nambane. So the first part, or the first mark will be on the 12, if it is on the positive side or positive axis. And then the second mark will be on 22.14, because it is the velocity that it leaves the ground with. But remember, we have positive marking for that. If the learner for that velocity it leaves the ground with from 4.2.3, if the learner got a wrong answer but then uses it correctly here, then the learner can get a mark. And then the second mark will be on 4 there. It is the velocity that it reaches the ground with, the time it reaches the ground. That will be the second mark. And then the fourth mark will be on what? The fourth mark will be on 4.2, because it spent 0.2 seconds on the ground. So the time when it leaves the ground will be what? 4.2. Okay. So the Nambane. Okay, first mark on 12. So we are going to go to criteria, but you wanted to do the markings, I see. Yes, the first mark on 12. Okay, second mark on 22.14 with correct, with positive marking from 4.2.3, and then on 4, and another one on 4.2. And then the other one will be the shape. We'll explain the shape when we get to the criteria. If we could move down. Now, if we take here, up has been taken as negative, please change the sign there. It is not up positive, it is up negative. So the initial velocity will be -12. That will be where the first mark will be. The velocity it leaves the ground with will be -22.14, positive marking from 4.2.3. And then the third mark will be on 4, the velocity it hits the ground with. And then the one it leaves the time it gets to the ground, and then the time it leaves the ground, because it spends 0.2 seconds with the ground. Now let us go to the criteria. The Nambane. So that is the marking criteria. Initial velocity indicated either positive or -12, depending on the direction that the learner is taking as positive. That will be a mark. Velocity it leaves the ground with correctly indicated there. It must be indicated, colleagues, from 4.2.3. Even that 12 must also be indicated. The time it reaches the ground, that is the 4 seconds, 4.2, or 4.2, and the time it leaves the ground, correctly indicated. Both the times that the number, we have decided that both of those times will be 1 mark. Now 4 and 4.2 will be 4 and 4.2 will be 1 mark. Both of them will go back to the marking there on the graph. And then the fourth mark will be on the shape. First line starting at 12 or -12, ending in the other axis. Is clear? Moving on to question number 5.2, the Nambane, because the acceptable labels, we have already done them in question number 2, colleagues. So to try and save time, we can move on to question 5.2. I said the components can be accepted for weight. So 5.2, learners were asked to use the principle of conservation of mechanical energy to calculate the speed of the crate at point B as it moves down. So for the correct principle, the learner will get 1. That is mechanical energy at point A being equals to mechanical energy at point B. And then correct substitution on the left-hand side, that is 10 multiplied by 9.8 multiplied by 6 plus 0, because initially from point A, the object was at rest, or at point A, the object was at rest. So that part will be 0. Then if that is indicated, then the learner must indicate that 0. The learner must indicate that 0, then that will be 1 mark on the left-hand side. And then on the right-hand side, we must have 0, because now at point B, the grade is on the ground. Then height there is 0. So we'll have 0 plus half multiplied by 10 multiplied by velocity that we are looking for. Then that will be 2 marks there for substitution. Correct substitution on the left-hand side, everything must be correct and the zeros must be indicated. Correct substitution on the right-hand side, the 0 must also be indicated. And then the learner will get a mark. The final mark will be velocity at point B, that is 10.84 meters per second. Okay. Then 5.3. Upon reaching point B, the grade slides along a rough surface BC and comes to a stop at point C, as shown below. Then we have the diagram there, 5.3. The learners are asked to define the term conservative, non-conservative force. So if any of the key weight is omitted in correct context, we subtract 1. So the definition, correct definition is force, underlined force is underlined there, for which work done in moving an object between 2 points depends on the path taken. So correct context, colleagues, if for instance a learner says a charge for which the work done, then that will be a wrong context, because the learner will now be talking about something else. Then there, the learner will get 0. But then if talks about something or omit that thing, work done in moving an object between 2 points depends on the path taken, then the learner can get 1 in that case. But if the learner substitute that force with any other thing, then the context will be lost, then the learner will get 0 in that case. Okay, but we are expecting them to get total for this definition. Then 5.4, learners were asked to write down the name of the conservative force acting on the grade between B and what and C. Conservative. A conservative force, if you could go up on that day, Nambane. The conservative force, it is the weight. And we must be careful here. Learners were asked to give the name. So if they were asked to give the name, they must give the name. If the learner gives the symbol, colleagues, the learner must not get that mark. I hope it is clear. The learner must not get the mark if the learner gives the symbol. It has to be weight or gravitational force or gravity. Then 5.5, here the learners were asked, what is the direction of the net force acting on the grade? Write down from B to C or C to B and give a reason for your answer. So here we are going to mark it in this way, colleagues. The correct answer is from C to D. Reason being, as it moves along BC, velocity of the grade decreases. Acceleration is in the opposite direction of motion, meaning it is going from C to what? To B. That is the direction of the acceleration. For the first 2 parts in the reason, then the learner will get 1 mark. When the learner talks about the velocity of the grade decreasing and the acceleration being in the opposite direction, that is 1 mark. And then the learner then uses the principle of, the formula of Newton's second law, where it says that net force is directly proportional to the acceleration and they are in the same direction. Then F net will go in the opposite direction, that is C to what? To B. So the last mark is where the learner talks or gives us the principle that relates acceleration and the net force, that is Newton's second law. And that principle says F net is directly proportional to acceleration and they are moving in the same direction, colleagues. So with that, that will be 3 marks. There is the other option that we have decided to accept, but it is on my memo that will be shared, where now the learner talks about the friction. Since friction, it is the only force acting on the object. And then we know, the first part will be friction is the only force acting on the object. F net is equals to what? Is equals to friction. Then the learner still there will then have to mention the principle that he or she uses
for her to conclude that friction is equals to what? The net force. They will have to mention that principle that according to Newton's second law, we know the F net is equals to MA and all those things, then friction net force is equals to friction is equals to the net force. Then that last mark will be where the learner uses the principle to show that friction is equals to what? Is equals to the net force. Then that will be the third mark that the learner will get. But if the learner just says friction is the only force that acts on the objects or on the grade along BC, and the friction is equals to the net force, for that part, that will be 1 mark only. Because the third mark, the learner has to indicate how did he or she conclude that friction is equals to what? Is equals to the net force. Okay, then that will be the question 5.5, colleagues. I hope it is clear. The second option will be shared as we share the amended memo, colleagues. Moving on to question 5.6. 5.6, the coefficient of kinetic friction between the surface and the grade is 0.15. Then 5.6.1, learners are asked to calculate the magnitude of the frictional force acting on the grade for 3 marks. So we are having the frictional force Fk is equals to mu k multiplied by the normal force, which is equal to mu k multiplied by mass multiplied by gravitational acceleration. We have mu k. This is a straightforward answer of question, colleagues. Then the learners will get 3 marks. 1 mark for the formula, 1 mark for substitution, 1 mark for the final answer. Then 5.6.2, I believe 5.6.1, we do not have any questions there. 5.6.2, learners are asked to state the principle of work energy theorem. Then here we are saying 2 or 0, colleagues. Everything must be there. Total or net. If total or net is not there, then the learner will get it wrong. Then the total net work done on the object is equals to the object's change in kinetic energy, or the work done on an object by a net force is equal to the change in the object's kinetic energy. This one is 2 or 0, colleagues. So it's either the learner gets total or the learner gets 0. All right. 5.6.3, if you could go up in that day, Nambane. So here we are giving positive marking from 5.2. So here learners are asked to use energy principles to calculate the displacement delta x traveled by the grade along BC. Traveled by the grade along BC. So we are going to use positive marking from question 5.2. That is the velocity it gets to point B with. And then the frictional force that they have calculated in 5.6.1. So option 1, energy principles, colleagues, we are not going to accept any principle other than the energy principle. If the learner chooses to use any other thing, then that learner must get 0. Here we want energy principles, meaning the learner can either use the work energy theorem or work done by non-conservative forces. So if they use the work energy theorem, then we are going to have W net is equal to change in kinetic energy. That is 1 mark for the principle. And then since frictional force is the only force acting on the object, then we'll have a substitution on the friction, work done by friction there. That is 14.70 that we got in 5.6.1. Delta x cos of 180 because it is acting opposite to the motion, being equal to that part will be equal to 1 mark. The whole substitution on the left hand side will be 1 mark, and then the substitution of the mass half multiplied by 10 for that part will be 1 mark, and then 0 squared minus 10.84 squared, that difference in velocity squared, that will be the second mark, and then the last mark for the displacement for the final answer of the displacement, that is 39.97 meters, colleagues. First mark on the principle, work net is equal to change in kinetic energy. Second mark on the substitution on the left-hand side, since frictional force is the only force acting on the object, then it means that work net will be equal to work done by frictional force. So substitution there on the work done by frictional force, 1 mark. And then on the right-hand side, we have 2 marks. The first mark will be on the first part of that substitution, that is half multiplied by mass, that is half multiplied by 10, that is the first mark. The second mark will be on the difference of the velocities squared, that is 0 squared minus what? Minus 10.84. Remember, the 10.84 comes from where? 10.84 comes from 5.2, colleagues. So if the learner got a wrong answer from 5.2, but used it correctly in here, you must give full marks. That is positive marking, colleagues. So delta X will be 39.97 meters. Option number 2 is where a learner now uses what? Work done by non-conservative forces. The only non-conservative force that we have here, it is what? Work done by friction. This is more or less the same as the option number 1. So we'll have 1 mark on the principle, work done by non-conservative force being equal to change in kinetic energy plus change in potential energy. And then the only non-conservative force acting on the crate as it moves along BC, it is frictional force. Therefore, that work done by non-conservative forces will be equal to work done by frictional force. Then substitution on the work done by frictional force, that will be 1 mark. And then substitution on the left-hand side, colleagues. Look here where the difference is. Here, the first part where now the learner calculates or substitute in the difference of the kinetic energy. That part where the learner substitute in the what? In the difference in the kinetic energies from point B and C. That is 1 mark. Then the second mark on the substitution on the left-hand side will be on 0, because now the object is moving on the ground. So there's no change in what? In height. And our height anyways is equal to 0 in any case. So that 0 has got a mark. So the learner has to indicate that 0. If the learner chooses to use this principle, then the learner for change in potential energy, the learner has to indicate that 0 there. So the first mark will be on the difference in kinetic energies from point B and to C. And the second mark on this substitution on the left and on the right hand side will be on the 0 that has been indicated, and the final answer will be on delta what? Delta X. That is that, colleagues. That is that for question number 5. I'm trying to rush, colleagues. I do not know if there are any questions for this question. That then Nambane.
Thank you very much, and that I'm happy. Let me check in the chat. If the learner rounded off 39.97 to 40 meters, do we award a mark?
Yes, I think we can award a mark for that, Ndate. Thank you.
Thank you very much, and that I'm happy. It says earlier, yes, we were told not to award marks for components of FG. Is there allowance for marks only for this paper, or we are going back to the previous version that FG or its components are accepted if the body is in an inclined plane?
Yes, it goes back to that issue of us saying we sometimes accept some of the things just for the purpose of this marking, colleagues. Hence, we should not share this marking guideline with our learners. We should not accept them, but then for the purpose of marking here, we will accept them, colleagues. It is just for marking here.
Thank you very much.
Like we have accepted the components on the applied force when in question number 2, where it is acting at an angle. So we accepted the components. So let us also accept the components for gravitational force. But that is not how we should teach our learners. So remember, when we draw the free body diagrams, learners must use the exact forces. But for marking here, we can accept, colleagues, but warn our learners that they should use the exact forces when they draw the free body diagrams. Thank you, Ndate.
Thank you very much, Ndate. I'm happy. I don't see any hands, so I believe we can go to question 6, Ndate. I'm happy.
Okay. In the meantime, as I present, can you please check with Mebusi and Ndate and Mezapi if they are attending to that issue that Ndate has raised. As I continue with question number 6 in that.
We'll make a follow-up, sir. Thank you.
Okay, thank you. Question number 6. Colleagues, that is where now we deal with Douglas effect. A patrol car with its siren on approaches an accident scene at constant speed. The siren of the patrol car emits sound waves with a wavelength of 0.2 meters. A person standing at the accident scene with a detector records sound waves with a frequency of that is 50 hertz higher than the one emitted by the patrol car. Okay, then a person standing at the accident scene with a detector records sound waves with a frequency that is 50 hertz higher than the one emitted by the patrol car. Take the speed of sound in air as 340 meters per second. So 6.1 learners were asked to state Douglas effect in weights. So we have part marking for this one, for this definition, colleagues. So the first part, the change in frequency or pitch of the sound detected by the listener, that is the first mark, because the sound source and the listener have different velocities relative to the medium of sound propagation. So the second part is there. Everything that is underlined must be there for each part, colleagues. First mark, change in frequency or pitch of sound, of the sound detected by the listener, that is 1 mark. Because where do we mark? Sound source and the listener have different velocities relative to the medium of sound propagation. That is the second mark. That is 6.1, that if we could go up. That the number, okay. And then 6.2, write down one medical application of Douglas effect. Medical application, colleagues, detecting the heartbeat of a fetus or detect where the arteries or veins are clogged. We have agreed that we will also accept if the learner just write Doppler ultrasound. Okay, that is 6.2. We move on to 6.3. 6.3.1, learners were asked to calculate the frequency of the sound waves emitted by the patrol car. Then they will use wave formula. That is V is equals to frequency multiplied by wavelength. We have speed of sound in air, that is 340, being equals to the frequency that we are looking for, and then multiplied by the wavelength of 0.2, and the frequency will be 1700 hertz. This one, it is straightforward like that, colleagues. And then 6.3.2, then we have positive marking from question 6.3.1. Here now learners are asked to calculate the speed of the patrol car as it approaches the accident scene. Remember, the person at the accident scene detects the frequency that is 50 hertz higher than the one emitted by the patrol car, meaning this patrol car is moving towards the accident scene. So we'll have formula, mark for the formula, Douglas formula, and then we have mark for substitution of frequency of the listener, the one that is detected there. And then it is said in the statement that it is 50 hertz higher than the actual frequency, or the frequency that comes from the patrol car. So the actual frequency, it is the one that we have calculated in 6.3.1, which is what? Which is 1700. So the detected frequency will be 1750. And then the substitution of the velocities there, it will be 340 over 340 minus VS. That is 1 mark, and the other mark in the substitution will be 1700. And frequency, speed of the source of the patrol car will be equals to 9.71 meters per second. I hope this one is clear, colleagues. 6.4. A scientist studying the movement of planets in the universe obtained results on Earth and planet Z as shown in the spectra diagrams below. We have two spectral diagrams there, colleagues. We are moving from F to planet Z. And then learners were asked to interpret the two spectra. Do these results indicate that planet Z is moving towards or away from Earth? And then learners were expected to explain their answer. The answer there is towards. And then the explanation, we have 2 marks or 1 mark for towards. The explanation, we have 2 parts of the explanation. In the explanation, first part is where the learner talks about the movement of the spectral lines as observed in the diagrams. So the spectral lines have shifted towards the blue end of the spectrum, which is the end of higher frequency or shorter wavelengths. That is the first mark, colleagues. When you look at your spectra on Earth and you compare it to a spectra on on planet Z, these spectral lines, and the learner must indicate spectral lines, they have shifted towards the blue end of the spectrum, which is the end of of high frequency or shorter wavelengths. So that is the first mark. The second mark, now the learner has to refer to Doppler's effect and relate that movement towards higher frequency to the movement. So according to Doppler's effect, increase in detected frequency, that shifting towards higher frequency indicates that planet Z is moving towards Earth or the Earth. So according to Doppler's effect, the learner has to mention that principle. According to Doppler's effect, increase or that shift towards the higher frequencies, so indicates that the planet Z is moving towards what? Towards Earth. That is the 3 marks on question number 6, making the total to be 14. That is that on question number 6, colleagues. And that number, I do not know if we have anything.
Thank you very much, and I'm happy. Let me quickly check on the chat. We do not have anything as yet. Colleagues, I don't see hands. Also, that is a confirmation that I'm happy that colleagues are happy with question 6. So I believe we can go to question 7 that I'm happy.
All right, thank you, Ndate. Question number 7. Learners investigate the relationship between electrostatic, that is Fa, and the distance between the centers of 2 positively charged identical metal spheres of equal magnitude. The learners change the distance between the metal spheres and record the electrostatic force the 2 metal spheres exert on each other. The results obtained in the investigation are shown in the graph below. We have the graph there, colleagues. So your dependent variable will be your net force, because that is what they want to see. And then they are changing the distance, which means that your distance will be your independent variable, hence it is on the x-axis. But here we have used the reciprocal of the distance squared. Okay. Now 7.1, learners were asked to write the name of the law physics law that was being investigated by the learners. So we are expecting Coulomb's law there, but the law is optional. The learner can leave it out, it's okay. But Coulomb's, then we can give a 1 mark for that. Then 7.2, learners were asked to write the conclusion that can be drawn from the results. So learners must not state Coulomb's law here, colleagues. They must write only the conclusion that can be drawn from the results obtained as shown in the graph. So the conclusion can be that the electrostatic force is inversely proportional to the square of the distance between the centers of the spheres. The electrostatic force is inversely proportional to the square of the distance between the centers of the spheres. Because, colleagues, here we talked about We talked about spheres. Then it is important learners mention centers. It can't be between them when we are using spheres. It is only between them is only accepted if we are talking about the particles, because they are very small. But here, because we are dealing with spheres, then learners must say between the centers. I hope it is clear, colleagues. So that is the conclusion. And
Mr. Moapi?
may I finish? Just hold it. Arisa, I will come back to you now.
Okay.
Okay. And then another option can be the electrostatic force is directly proportional to the reciprocal of the square of the distance between centers of the spheres. That is 2 marks. If we could move on to 7.3, we are almost done with question number 7, colleagues. That number, if we move on to question 7.3, I would like when we take questions, we take for the whole question. Yeah? Okay, question 7.3. The gradient of the graph obtained is found to be 2,025 times 10 to the power negative 8 newtons meter squared. That is the gradient of the graph that we have there. Then learners were asked to calculate the magnitude of the charge on each sphere. Remember, these charges are equal in magnitude, colleagues. Yeah? So the gradient, we know when we are given a straight line graph, the gradient will be what you have on your y-axis. That is your dependent variable over your independent variable. So that is the gradient, colleagues. So when you look at Coulomb's formula, we have F is equals to KQ1 Q2 over R squared. And then if you look at the gradient, if you take 1 over R squared and then take it to the other side, you divide by it, then that will be the gradient. Again, in our graph on the y-axis, we are having electrostatic force, and then on the x-axis, we are having 1 over R squared. So that gives us the gradient. And then that will then be equal to what? You'll get 1 mark for substitution into that. That will be another mark. We don't have the mark for the answer of the electric field at, due to X. We do not have a mark there. And then the other mark will be on the substitution into the formula to find electric field due to what? Due to Y. Then that will be the second mark. With the substitution, everything must be correct, colleagues. Everything must be correct. Then, after finding the electric field due to each of the charges, then E net is equal to EX plus EY. So we'll then not have a mark on that formula, then we'll have a mark on the substitution of the answers, even if they are wrong, colleagues. Even if those answers are wrong, but if they are correctly substituted there. By correctly substituted, we mean that then if they have taken right as positive, then E due to X will be positive, and then E due to Y will be negative. If the learner has done that, then that learner will get a mark in the substitution. And then the last mark will be for the final answer, where we are expecting them to give both magnitude and what and direction, because the question was clear that they should calculate the net electric field, not the magnitude of the net electric field. So they must give, or rather that mark will only be awarded if the magnitude and direction have been given. Okay, that is 8.3. If you could move down that day, Nambane. Or left, it becomes relevant. The issue of direction only comes relevant there at the end, where we substituted the electric fields that we have calculated earlier, colleagues. Because in the formula, remember when you calculate the electric field, we do not include the signs of the charges. So this negative, or rather the change in direction, will only become relevant down there, where now electric field due to X, because it is going to the right, will be negative, and the one due to Y, because it's going to the left, will be positive. Then we will have your answer there as is it 52,968.75 newtons per coulomb to the left. Magnitude and direction, colleagues, both of them must be there, then you get a 1 mark. That is that for question number 8. We will now be moving to question number 9. But I think I saw a hand earlier there, colleague. So if we could allow, I don't know if it is mere alert or something. Yeah, I think it is mere alert and that the number.
The hand is
Yes,
it's me, Alta.
I'm
Yes.
sorry I was struggling to get a sign. Yes, it's me. I want to go back to 7.2 Coulomb's law. When we look at the definition given in exam guideline also, we cannot say to the center of the sphere. It's up to the surface of the sphere, because there's no charge inside a sphere. So that one must be corrected there. And then I want to know if a child says towards Y at this question that we're currently busy with 8.3, instead of to the left. Y is to the left. Can we accept it? Thank you.
All right, thank you very much. I think the first one was just a comment, Me Alta. Thank you very much for that. And then 8.3, you are saying if instead of using left, they are using what? That number, is it east or west?
They say towards Y, which is left of it.
They said towards Y, yes.
Towards Y. Okay, let us accept it, colleagues, any other direction that is given. I'm looking at the question or the statement here. You see that part where it is to the right. But it's fine, colleagues. I think we can accept any other direction conversion that the learner uses as long as it is correct. Meaning, even if to the right there they use east, even if they use west, like May is saying, if they use towards something, then that will also be correct as long as it is correct. Okay.
Thank you very much, Alta. Thank you very much, and that I'm happy. I don't have anything on the chat in that day, so it basically says we can continue.
All right, colleagues, let us move on to question number 9, the last question here. Question number 9, that is on electric circuits. The battery in the circuit below has an EMF of 15 volts and negligible internal resistance. The two identical resistors R1 and R2 with resistance R respectively are connected in parallel to each other, and bulb C with resistance 3 ohm is connected in series to the battery as shown below. The resistance of the connecting wires, switches, and ammeter is negligible. Now the first question, colleagues, learners are told that both switches are open, and then 9.1.1 they are asked to determine the reading on V1. Reading on V1 it will be 15 volts, and the reading on V2 will be 0 volts. But even if for 0 volts, you just write 0 there, then it's fine. Okay. Now the question continues. It says both switches are now closed. The amount of charge that passes through bulb C in 3 minutes is 540 coulomb. Then 9.2 learners are asked to state Ohm's law in what? In weights. And then here we have, if any of the key weight is omitted in correct context, we subtract 1 for each. So it can be 0, 2 or 0, or it can be 1 out of 2, colleagues. The potential difference across a conductor is directly proportional to the current and in the conductor at what? At constant temperature. So if any of the key weight is omitted in correct context, we can subtract 1, colleagues. Okay. Then 9.3 learners are asked to calculate the reading on the ammeter. Then the reading on the ammeter, as you can see, the ammeter from its position there, it measures the total current, and that current that it will measure with both switches closed will be the current that will have passed through what? Through bulb C. So we can use the charge in bulb C and the time there to calculate. This is from grade 10. That if we could go up a bit. That the Nambane? Okay, so we can use the formula from grade 10. Current is equals to charge over delta T. We have the charge there is straightforward, but your time must be in seconds, so it will be 3 minutes multiplied by 60. Then that whole substitution is 1 mark, and then current arona will be 3 amperes. So 3 marks there. Question number 9.4. Now learners were asked to calculate the resistance R of the 2 resistors. We have 2 options, and then in my memo I have the other option, colleagues, that we will share with you. But the thing is, if you can see that the final answer is correct, just try and go through what the learner has written and check if the science is correct there. If everything is correct, then we can award a mark. And then, like I indicated earlier, if you come across any of the options that are not indicated in the memo and you feel that they are correct, just share them with us, and then we'll put them in the addendum. So option number 1, colleagues, for learners to calculate resistance R, You can start first by calculating total resistance, which will be the total potential difference and total current from the previous question, which is 9.3. And then after calculating the total resistance, they can then find the resistance in the parallel combination of the parallel combination, because we know the parallel combination, the resistance of the parallel combination plus resistance of the bulb, they will have to give you what? They will have to give you the total resistance of the circuit. Then the R parallel will be equal to what? Will be equal to 2 ohms. Then 1 over R parallel will be 1 over R1 plus 1 over R2. Then it will be 1 over 2 calculated there, being equals to 1 over R plus 1 over R. And then the final answer for resistance will be what? Will be 4 ohms. So where do we put the marks? Ohms formula, Ohms law formula, that is R is equals to V over I for total now, where the learner now looks for total resistance, 1 mark. Substitution into that formula where they use total potential difference or the EMF, 15 over 3, 1 mark. 3 that is calculated in question 9.3. So if it is wrong but used correctly in here, then the learner can get this mark, the second mark. The third mark is where now the learner calculates for R parallel by subtracting total the R, the resistance of the bulb from the total resistance. Then in that substitution, then the learner will get 1 mark. And then another mark will be now when the learner substitutes in the formula to calculate the resistance for R parallel, that is 1 over 2, 1 mark. So if the learner then attempts to calculate R parallel, but they calculate it wrongly, but then they use it correctly in here where you have 1 over 2, then you can award that mark. And then the second mark here on this formula of the parallel combination will be when now the learner substitutes for R1 and R2 with R and R. So it is 1 mark and the final answer, which is 4 ohms. All right. Then option number 2. Now we have a situation where now the learner looks for what? For the potential differences for the R, for the parallel combination. So the learner can calculate the potential difference across the bulb. Potential difference across the bulb, which is C, will be what? Resistance of C and the current that goes through C. It is what? It is 9 volts. And then the learner goes on to calculate potential difference across the parallel combination. Then that will be the total potential difference minus the potential difference across what? Across the bulb. Then that will be what? That will be 6 volts. Then the learner goes on to calculate R parallel. So there is no mark for calculating V parallel. The mark will be on calculating R parallel. So the learner will then calculate R parallel. And then if the learner goes on to substitute that value of 2 ohms correctly in that parallel combination formula to calculate R, then we'll have 1 on the left-hand side and then 1 on the right-hand side, provided that all the resistors have been substituted correctly. And then the resistance there must be what? 4 marks. Like I indicated, I have another option that we will share with you colleagues later. But just look, if the learner ends up with 4 ohms, then it is most probable that the learner must have done something correct up there. Just go through the answer of the learner, and then I believe the learner will get some of the marks. But we'll share the options as we get them, colleagues. Thank you. That can we move? Question number 9.5. Now they say only switch S2 is opened. If switch S2, only switch S2 being opened. 9.5, how will this influence the reading on the ammeter? Choose from increases, decreases, or stays the same. The answers should be decreases. And then 9.6 says explain your answer to question 9.5. We said, colleagues, we should not use negative marking from 9.5 here. With switch S2 opened, what will happen is with switch S2 opened, that R2 will not be effective. Then it means we have removed one branch of the parallel combination. Then we'll have our total resistance, or having our resistors, which will be R1 and the bulb, now connected in series. We know once you increase resistors in series, then it means total resistance of the circuit will increase. And according to Ohm's law, it is important that learners refer to the principle, colleagues. This second mark, learners must refer to the principle that they use, colleagues. So according to Ohm's law, or rather they can just write the formula R total is equals to V total over I, for constant V total. If RT increases, then IT will do what? Will decrease. So the second mark there, the learner has to talk to the principle, and because they will be comparing what total resistance and total current, then it means potential difference must be kept constant. That part also is very, very important, colleagues. Where they say total potential difference is constant, also must be there. And then R total, then they give the relationship between total resistance and total current. That whole part must be there for the learner to get what? To get 1 mark. Might seem too much, but that is how we have decided to mark it, colleagues. I hope question 9 is clear. If not, we will allow for any clarity-seeking questions, colleagues, now.
Thank you very much, and I'm happy and nicely done. Maybe it's only because of network problems that we have in different areas, and that I'm happy. Some colleagues are asking questions in, let's start with 8.2. These are the ones now coming from the chat as well as the YouTube, for those that are watching from YouTube. The very first one is now at 8.2. If a learner labels the force diagram using Fx and Fy instead of Ex and Ey, do we award a mark or not? Not forgetting the definition of the electric field.
So the question also says not forgetting the definition of electric field.
Yes.
Okay. So here, learners were asked for a vector diagram, not the force diagram. Okay. Yeah. If we are being lenient, colleagues, maybe we can penalize once, man. We can penalize once, because here we were looking for electric fields. Let us penalize once and then give the other mark and the second mark. That is Nambane. That is my feeling.
Okay. 8.2, colleagues, let's penalize once if a learner used now Fy and Fx. The other one that is at now 6.1. And
okay.
At 6.1 it says, can we accept the definition from the department books for 6.1, as Doppler effect is the change in frequency of the sound detected by the listener due to the relative motion between the sound source and the listener?
Yes, we can accept that. We can accept that. Yes, thank you, Ndate.
Because it is from our terms and definitions, so we can accept. And I am looking into another one. Okay, no, that's basically it, that I'm happy. Colleagues, inputs, anything? Let's just note that the addendum, Tatema Humapelo, kindly switch off your video, please. Let's just be on the lookout that a new updated memo will be available, colleagues. I did send a register earlier on, kindly complete. You maybe also got it from your subject advisors. Colleagues, for those that are asking now for us to go to question 1, question 2, the recording is available, and you can just maybe play the recording on YouTube again, just maybe to see the parts that you believe or feel that you missed, because now we're supposed to start now with technical science at 11:30, but the challenges now that we had obviously prolonged this particular meeting, so we will not be accepting any other questions because we are going to use now the very same platform for streaming the TechSci and as well as the recording. So colleagues, from me to you and Datem Happy and all the colleagues that are here, thank you very much for all the efforts. Let's meet tomorrow now for paper 2. Colleagues, we start at 8 o'clock in order for us now to be able to do things in time. So we start at 8 o'clock, so I will later now share the links with the subject advisors, and then let's meet tomorrow in the morning for paper 2. That I'm happy. Thank you very much.
Before you rush out, I just want to
Yes.
indicate that we have not forgotten your question. That we'll come back to you, colleagues. That had a question in question 4. That the one that I referred to, that to look at it. We'll come back to that question. That don't despair. From my side, I would like to thank you very much, colleagues, for your patience. We had troubles earlier, but then you were here with us up until now. Thank you very much for your patience. Until next time. Thank you.
Thank you very much, and that I'm happy. Colleagues, have a lovely day.
Bye.